Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen, and also students. Welcome to the guest lecture on chemistry of membrane. This lecture is presented by Department of Chemistry, 10 November Institute of Technology. First thing first, let me introduce myself. I am Zeni Rahmawati, and in the next 1 hour, I will lead our discussion on the very interesting topic, the application of gas separation membrane. Before we get started, please kindly register your attendance today by clicking on the registration link in the chat feature. Okay, now I would like to introduce our speaker. Our lecturer comes from very far away. At the moment, he is working at the Materials Concept and Reaction Engineering Group in the School of Engineering at Newcastle University. Together with his group, he has published many papers on membrane, chemical loopings, and catalysis. He obtained his undergrad from the University of Aberdeen, Scotland, United Kingdom. He got his master from the same university and also University of Turin, Italy. And I am very proud and very grateful that we were doing our PhD in the same lab at University of Aberdeen. I can say that he is a very wonderful friend and great teacher. So please welcome Dr. Greg Mudge.
Thank you very much, Zeni, for that very kind introduction. That's very nice of you. And just let me start by saying it's a great honor to be able to speak to you all today. So I'm just going to load up my slides. Give me 2 seconds to do that. So hopefully you can all see that. If there's any problems with the sound or the slides or anything like that, just interrupt me. I'll try and leave lots of time at the end so that we can have a lot of discussion. I'm very happy to take any questions. So yes, first of all, just thank you again for the kind introduction and for the opportunity to speak to you all today. As Zeni mentioned, I'm going to talk about membranes for gas separation. I guess I'm going to start with an introduction to membranes, sort of quite generally, membranes for gas separation processes, why we need to think about chemical separations at all, really. Then I'm going to talk about my recent research over the last sort of 3 or 4 years. And then I'll finish with what I consider to be some of the maybe future challenges or future opportunities for membranes in the area of gas separation. So before I start, you'll see a large number of names on the slide here, and you'll see a large number of institutions. As Zeni mentioned, I'm at the Materials Concepts and Reaction Engineering Group in Engineering in Newcastle University. But the work that I'll talk to you about today includes contributions from University College London, the Faraday Institution, University of Zaragoza in Spain, and also Imperial College London. So I just want to acknowledge the contributions of all this big list of people here at the start before I go into the research. So Zeni's already done this, so I'll fly through this very quickly. As she mentioned, I did a chemistry and a chemical engineering degree and then PhD in Aberdeen. And then since I left Aberdeen, I've been what's called an EPSRC Doctoral Prize Fellow. And then at the moment, I'm a Newcastle University Academic Track Fellow, which is a sort of transition fellowship from being a researcher to an academic. And I've also got the Royal Academy of Engineering Research Fellowship. And if we look across the work that I've done in the last sort of 5 to 10 years, I think my interests are basically captured by this statement here. So sorbents and membranes for chemical separation processes, particularly carbon dioxide capture, as well as materials characterization, all the way from the molecular scale to the device scale. And what I mean by that is I'm interested in things like in situ IR spectroscopy, where we can look at individual molecules adsorbed on a surface, all the way to looking at an entire device, so looking at a membrane module and how it works in practice. As Zeni mentioned, I've been lucky enough to publish in a number of journals. Examples of these are given at the bottom, and if there's anything of interest to you today, I would just encourage you to either look it up online or just contact me, and I'd be very happy to send you any of the publications. I also just wanted to introduce my current team. I'll be talking about some of the ideas that they're working on, and also some of the current funding to give you an idea again about the interests I have in the work that I'm doing. So my Royal Academy of Engineering Fellowship runs until 2025, and I'm interested here in facilitated transport membranes for carbon dioxide capture. We currently have a UK Catalysis Hub research grant with colleagues in Aberdeen that both Senny and I know very well. And here we're interested in converting carbon dioxide to methanol using a membrane reactor. And this person in the bottom right here, Guanan Chen, he's employed on this UK Catalysis Hub research grant. Very recently, it's only just started in the last month, we've got a very large scale EPSRC program grant. So this runs for 5 years and it involves 6 universities and 12 companies in the UK. And in this program, what we're interested in with all these different partners is different chemical separations using membranes. And this could be in the area of food, medicines, drugs, energy, industrial separations. We're interested in working together across applications, across different types of membranes. So this is a very large investment in membrane research in the UK. And then the people along the bottom, this is Jackie and Imran. They're both PhD students that are just finishing their first year. Taran is due to join us later this year. He's just taken up a PhD studentship. And then Pedro and Guanan are the postdocs that work in this area. So I just thought I'd like to introduce them before we start. So now I want to get into why chemical separations are important. I think it's something that we all take for granted. We don't acknowledge that chemical separations are running 24/7 around the world constantly to provide all the products from, you know, the mobile phone that we all have to the gasoline in a car or the kerosene in a plane. There's distillation columns running around the world constantly. And for this reason, 10 to 15% of global energy consumption is used or consumed by chemical separation processes, which is very significant and perhaps surprising if we don't spend our days thinking about chemical separations. They also account for between 40 and 90% of capital and operating costs in industry. So the chemical industry in particular, a large percentage of the money they spend for building chemical plants and operating chemical plants is used up by separation processes. And we'll talk about what they might be in the next slide. That said, even though they use a large amount of energy and they cost a lot of money, the National Academy of Sciences, this reference at the bottom of the slide here, National Academy of Sciences describe chemical separations as often overlooked and underappreciated. And that's the point I'm trying to make here, that we don't go around every day thinking that, you know, the car that we're driving or the phone that we're using, the components there have been through chemical separations. And they also pointed out, and I think this is important today because I'm coming to you from an engineering department and I'm speaking to a chemistry department. They also point out that the chemistry and particularly chemical engineering communities need to seek to work better together. We often work on similar problems, but we use different language to describe the same thing. And this image on the right here, I think, captures the point I'm trying to make quite well. There's 90 natural elements and 31 of these are used in manufacturing a smartphone. Okay, so the average smartphone that we all have in our pockets, 31 natural elements are used. Of these, there's some of these elements, we have lots of them, that's fine, but some of these are under serious threat. They're going to run out very soon. So if we take that forward one step, what does that mean? It likely means that in the future, we're going to have to go through the waste of, you know, laptops, mobile phones, tablets, and recover these elements through a separation process, so that we can continue to use these materials sustainably. And then this periodic table on the bottom here, what I'm trying to show here is that we're now starting to think about how can we recover useful metals. So example being like lithium for lithium-ion batteries or uranium down here for nuclear reactors. How can we recover that from seawater? There's 3 orders of magnitude more uranium and lithium in the sea than there is on land. But in the sea, they exist in the parts per billion concentration. So very, very difficult separation process, but something we may need to consider in the future. And the same thing can be said about land. Again, I've mentioned mobile phones. So these are all the elements that are used in making a mobile phone. And the same can be said about the air. If we think about carbon dioxide removal from the air, maybe methane removal, nitrous oxide removal, there's lots of separation challenges, in my opinion, that are sort of coming over the hill. And then the squares, the triangles, and the circles, these indicate elements that are used in batteries, catalysts, and magnets. These are important now. But as we go towards a more electrified industry and electrified society, they're going to become even more important. We're going to have battery vehicles. We're going to have catalysts and fuel cells, for example. So all of these elements typically exist on the order of ppm concentrations in the Earth's crust, and we have to extract the rock and then through a separation process to get the elements we want. And it's very energy intensive. So I just want to start by saying basically chemical separations are very important for many of the things that we take for granted. So then the obvious question is, how do we do chemical separations? So here I've got, again, a plot or a picture that's came from the National Academy of Sciences report. We're all very familiar with distillation. Distillation has been practiced for centuries. We can go back hundreds, if not thousands of years and find examples of distillation. We're all probably familiar with drying and evaporation, etc. These are all very high energy separations. They rely on the application of heat and differences in, for example, the enthalpy of vaporization. Very energy intensive way to do a chemical separation. If we go all the way down to the other end, low energy, and I'll pick on membranes because that's what I'm talking about today, we can, in principle at least, have lower energy chemical separations. So I work in this area in the middle here. I work with adsorbents, absorbents, and membranes. And one of the reasons that I work in this space, and I think it's important, is if we look at this plot here, again, this is where the 10 to 15% energy consumption figure comes from. If we used membrane-based separation processes in the chemical industry to replace distillation, we could get approximately an order of magnitude reduction in the amount of energy that we use to perform chemical separation. So moving from thermal chemical separations to non-thermal separations is a very important challenge for both researchers and within industry. So if we know that chemical separations are important and we now have a bit of an idea of how to do them, how does nature do a chemical separation? What's maybe the ideal way of doing a chemical separation? So here I want to pick on examples from nature. These are sort of cell membranes. We see we get different types of transport. We get simple diffusion, facilitated diffusion. There's specific transporters that pick things up from one side, pull it through and release on the other side. And then in the final image, you see a beautiful parallel pore, this like exactly straight, perfectly parallel pore that allows something to pass through with no restriction, no limitation on its transport. And this quote, I think, basically tells us what we should be aiming for if we're separation scientists. So the potassium ion channel in a cell membrane is thousands of times more permeable to potassium than sodium, despite the smaller size of sodium, and it exhibits permeation rates approaching the diffusion limit. We can't really do any better than that. We've got great selectivity, thousands of times higher selectivity for something that's larger, a larger ion, but also the diffusion, the transport is approaching the diffusion limit. It can't go any faster. So very high selectivity, very high rates of transport. And it's all to do with these specific interactions, specific chemical interactions and structure, this nice, beautiful parallel pore. And this is also what the National Academy of Sciences tell us, that we need to design separation systems that have high selectivity, high capacity, high throughput. And basically, we need to do this by understanding the materials and the processes that we use. So just to summarize just this first little bit very quickly, I've tried to cover why chemical separations are important, how we do them, so using things like distillation, sorption, and then perhaps a better way to do things, low energy chemical separations using membranes, and perhaps we can also get inspiration from nature about how we might design systems to do that. So what I'm going to do in this middle section is I'm going to talk about gas separation membranes generally, their applications, the materials they're made from. Then I'm going to talk about supported molten salt membranes. This is the class of membrane that I'm interested in. And then I'm going to finish talking about future gas separation challenges for membranes. So this is just a simple list of various applications that gas separation membranes can be used in. If we look at the first three, we see here that we're thinking about hydrogen production, basically, or some sort of industrial reaction engineering, adjusting syngas ratios. Then if the next example is air separation. So producing high purity nitrogen, high purity oxygen. And we're thinking about hydrocarbons. So I've already mentioned about potentially if we could replace distillation approaches with membrane approaches for producing different categories of hydrocarbons. You can see that we're also interested in helium separation, helium recovery. I think this is going to be an increasingly important separation process. We're slowly losing helium, right? It's very light that just once it's released, it goes away and we don't get it back. So I think there's going to be an increased focus on helium capture and helium separation in the future, helium recovery rather. This is not an exhaustive list. It's just wanted to give some examples of the different areas. A recent example that I've found quite interesting is the idea of producing oxygen for ventilators. We're all very familiar with the need for ventilators due to the COVID-19 pandemic. So people are now thinking about how can we use one of the advantages of membranes, which is a small device. In principle, you can intensify devices and make them smaller. So how could we produce oxygen for use in medical settings? If I pick the first example here, which is sort of hydrogen production, generally speaking, or hydrogen separation, just wanted to talk about the different classes of materials and the different potential applications and the different properties of these materials. So we can use dense polymer membranes. So this is essentially just a non-porous piece of rubber, almost like a wall of a tire or something like this. Microporous ceramics, so ceramic materials with very small porosity. We can use dense ceramics, so they don't need to have porosity. We can get gas transport through ion conductors, so potentially oxygen ion conductors or proton conductors. We can use porous carbon materials. We can use dense metallic membranes. So these are probably the most famous or most popular membranes for hydrogen production, palladium-based membranes, where hydrogen adsorbs on the surface, separates into protons and transport through the solid metal. So I just want to show that there's opportunities for lots of different people with lots of different specialities, whether you're a polymer chemist, an inorganic chemist, if you're interested in metallurgy, there's opportunities for designing and improving membrane processes. And I also wanted to point out that they have different application opportunities. So if we're thinking about polymers, typically we're in the range of approximately 100 degrees for obvious reasons. We don't want to decompose the polymer. If we're looking at ceramic membranes, we can go to very high temperatures, even above 1,000 degrees with some materials. And if we're looking at metals, we're typically in that intermediate temperature range. And this dictates the type of application. So, for example, ceramic membranes and metallic membranes, because we can operate them at high temperature, we can start to think about chemical reaction engineering, so separation and reaction using catalytic membrane reactors. And obviously they have different properties. They've got different properties in terms of selectivity, flux, issues around poisons. Different gases will cause the membranes to fail depending on which membrane you use. So lots of different opportunities and lots of different challenges. And this is just for one application. This is just for hydrogen. If we then look at a different application, this is now air separation. So trying to produce either high purity oxygen or high purity nitrogen. I just wanted to move from talking about materials to talking a little bit more about the process. So in this first example, we've got a one-stage membrane separation process. We've got an air feed gas, goes into the membrane module, and we get oxygen depleted air. Some of the oxygen has gone through the membrane, and we've made oxygen enriched air. But you can see that we've only got to 30 to 60% oxygen, or conversely, we've gone from 21% down to 10 to 15%. So we haven't pulled all of the oxygen out of that stream in a single membrane module. However, if we move to a two-stage separation process, and this second stage separation unit could, in principle, be a membrane, it could be a sorbent, it could be some other sort of separation process, we can get to pure gases, so pure oxygen in this case. And the point I want to make here is that membranes generally have been considered as a high throughput, small footprint separation process, but not necessarily for very high purity outputs. You typically need multi-stage membrane modules to get high purity outputs, at least with the types of materials that have been used to make membranes for the last 10 to 50 years. And that might be starting to change based on some of the materials that are now in production. So now I want to move on to my particular interest. So this is carbon dioxide capture. I've talked about hydrogen, I've talked about oxygen. So now I'm going to focus on carbon dioxide. So I mentioned I've used some of these terms before, and I'm assuming you're familiar with some of them, but I will go into detail in a minute. But basically there's different properties that we need membranes to have. We need membranes to be selective. So if I have a mixture of carbon dioxide and nitrogen, I need the membrane to be selective for carbon dioxide. And I need my membrane to be very permeable. I need it to transport a lot of CO2, in this case, through the membrane in a given amount of time. So here we're interested in the amount in a given amount of time, basically, simply speaking. But due to various aspects of the process, we don't want necessarily membranes that have infinite selectivity or infinite permeability. In certain applications, we have optimum properties that we want, driven by the application itself. If I have to apply pressure to my feed gas to force carbon dioxide through, I need this sort of optimum operating window for that process overall at a large scale to make sense. And you can see that for a long time, there was basically one type of membrane that would fit this properties perfectly. This is the Polaris membrane, which is now commercialized. You can buy this from a company, and it's used for separation processes such as separating CO2 from methane, so natural gas cleanup. So the point is that we need to manipulate the membrane, manipulate the way that we make the membrane, so that we can achieve properties that are actually useful in a real practical application. And the way we can do that is we can start to think about, for example, the area of the membrane and how we control this area. So in this example here, it's highlighted in a blue square. We can think about the thickness. We can think about the materials the membrane's made of. And in this way, we can start to play around with the properties of the membrane and improve it for that certain application. And I also want to use this slide just to explain that a lot of membrane processes, you need a driving force to force transport through the membrane. A lot of membrane processes use the application of pressure in the feed stream, pressure on the feed side of the membrane. All of the membranes I'll talk about from this point on, all of my work, we use a partial pressure difference, not an absolute pressure, so a partial pressure difference. And we use a sweep gas on the permeate side to create that difference. So in the feed stream, you see we have some CO2 mixed with nitrogen. Our sweep gas contains very little or no carbon dioxide. So it could be something like steam, it could be an inert gas like nitrogen or argon. But the point is that you can see here the driving force acts across the membrane because we have a difference in partial pressure of CO2. We don't have an absolute pressure. So everything I'm going to talk about is all happening at atmospheric pressure. There's no pressure in the feed stream. As I mentioned, I'm interested in supported molten salt membranes. And I want to introduce what these are briefly before I talk about some of our sort of recent results. So first of all, a molten salt. I'm talking about carbonates, nitrates, hydroxides, typically made from lithium, sodium, potassium, just common inorganic salts that you would use for lots of different things, from food to medicine and every day in the lab. So if you want to think about just lithium carbonate for the rest of this talk as the molten salt, then that'll work, and that's fine. So we've got a molten salt. So we take this inorganic solid and we heat it up to a point where it melts. So all of these membranes that I'll talk about for the next little while are all operating above 400 degrees. We take that salt, that solid salt, we infiltrate it into the pore space of a ceramic, and I'll show you images of these in a minute. We infiltrate it into the pore space, we heat it up, and that salt melts. So we have a supported liquid membrane, or a supported molten salt membrane. So in the pore space, there's a liquid phase. We can have the solid can be made of an inert ceramic, something like alumina. And then in this case, carbon dioxide will react with the molten salt phase to form a carbonate ion. It can be transported through, and then carbon dioxide released on the opposite side of the membrane. We can use an oxygen ion conductor for the solid phase, and this would result in a different permeation mechanism. Or we can even use an electron conductor. So we can build these membranes out of metal. You could build this out of a porous stainless steel or porous silver, for example. And in that case, you can co-permeate carbon dioxide and oxygen in a fixed ratio. So to make that carbonate ion, we need a half oxygen for every CO2. So we can permeate CO2 and oxygen in a 2-to-1 ratio. So that's quite interesting for controlling the ratio of two gases that pass over a membrane. If you're interested, there's this review paper that was published in 2019. This talks about all the different properties, all the different applications of supported molten salt membranes. But the point I would really want to stress, and the reason that I work on these membranes and that I'm interested in them, is that in this plot here, we see permeability, so how permeable the membrane is for CO2, versus selectivity. And if you look at these diagonal lines, the 2008 upper bound and the 2019 upper bound, you see that there's a trade-off in this behavior. So if you have a high permeability membrane, typically it has lower selectivity. And conversely, if you have a high selectivity membrane, typically it has lower permeability. This is a fundamental trade-off in almost all classes of membrane. It's not a trade-off in a supported molten salt membrane. And the reason for this is that the molten salt has almost infinite selectivity. There's about 3 orders of magnitude difference in solubility of carbon dioxide and nitrogen in the molten salt. And then it has extremely highly mobile carriers. These carbonate ions are in a liquid at 400 degrees, so they have very, very high diffusion rates. So high diffusion gives you high permeability and extremely high selectivity, up to around 1,000. So we're operating in this very interesting region here, where there's basically no other membrane materials that can operate here. It's a very different way to build a membrane, and they're very new, very interesting, and very exciting. So I want to talk about some of our sort of technical work, some of the things we've been doing the last couple of years. We're very interested in controlling the geometry of membranes and the shape, the size, the porosity, because all of these properties have an impact on transport. I already talked about the idea of having a perfectly straight parallel pore, so that a molecule moving through the membrane can just go straight through. There's no resistance to transport. So this is one of the key challenges that we work on. How do we get a high density of parallel, aligned, connected pores? So these are the properties we want. If we start in the bottom image on the left here, this is just something like alumina, a ceramic material that's been pressed into roughly the shape of a coin. The porosity in here will be very, very contorted, very tortuous, very difficult for the molecule to move through. Whereas if we move up these series of different preparation techniques all the way to using a laser to drill small holes in a ceramic, we can form these sort of perfectly cylindrical pores with a straight through transport. And this is laser drilling. We've also looked at laser directed solidification. So we grow composite ceramic. We then use an acid to etch out one of those ceramics, and then we fill the pores with molten carbonate. And these images here are X-ray CT images of the internal structure of the membrane. So in the gray, you see the ceramic, so this gray color here. In the black, you see the pores, so it's actually empty space signified by this black. And then we can do lots of different visual reconstruction techniques, computational techniques to analyze connectivity, permeability, tortuosity, etc., etc. We can understand by looking inside the membrane using X-ray tomography the sort of properties that we're giving these structures. We're also very interested in using what I would term a model membrane. So we want to make membranes that are useless for the real application, but they're very, very useful in the lab to tell us about performance and how these membranes operate. So I picked one system here that I think is quite interesting. This is just a ceramic crucible, so a small ceramic crucible that you would use in the lab to do some sort of inorganic synthesis. We then laser drilled lots of little pores in the bottom, so you can see these little pores here and here. And then this image in C is like a cross section. If we cut through this, we cut through the structure, this is what you would see. So you've got these laser drilled pores, and then we fill the crucible with molten salt. So we can fill it with a lot, or we can fill it with very little molten salt. And what we have is a structure or a membrane that we have very high surface area on the permeate side, very low surface area on the feed side, and we can vary the thickness without changing the surface area of the membrane. And then we can swap the way we feed the gas as well and change the surface area for the feed and permeate side. So we can get lots of useful information about the transport mechanism using structures like this. And in this particular case, we found out that the permeate side surface area of the membrane is the rate limiting step for transport across the membrane. So CO2 comes in, it diffuses through, and it leaves the membrane. The surface area on this side of the membrane is the rate limiting step. As I said, these model structures are no use for a real application, but we can take this knowledge and apply it in a structure that is useful. So this image here is a ceramic hollow fiber. So just think of a very small, like a plastic drinking straw structure. We use the knowledge from here to build a better membrane. So you see on the image on the left in the blue, we have a very, very low surface area for desorption due to the way that we've filled the structure with carbonates. We've filled all the porosity. Whereas in this image, we've deliberately left a lot of open porosity, and the blue color is the molten salt. And this allows us to have a very high surface area for desorption, which we know is the rate limiting step from the model system. And then when we look at permeation rate, we see that we can get higher permeation rates. So we use a model system in the lab, a very simplified structure that is never going to be a scalable membrane, but it tells us information about how the membrane operates. And then we use a real structure, a real scalable membrane structure, and apply that knowledge to make membranes that are more useful for real applications. So in that past slide, I was talking about how I control, or how I try and control, keeping the molten salt in a specific part of the membrane where I want it to be, because that will give me better performance. But we all know that liquids tend to spread, they tend to wet, they tend to move around in an uncontrolled way. So how can we exploit that behavior to have something advantageous in our membranes? So if you focus on these images in the bottom left to start with, this is a contact angle furnace, so a high temperature furnace. We control the gas atmosphere, we take images, and we see the molten salt wetting and starting to spread on the surface. So as we increase the temperature, we see the molten salt wets the surface. So this means at high temperatures, the molten salt likes to move, it likes to spread around, and we can use that to our advantage. So I mentioned the supports for these membranes are typically ceramics. Ceramics have the problem that they're very brittle, they're not very strong mechanically, they tend to snap and crack and break. So we designed a system where we deliberately introduced a great big hole in the middle of the membrane. So we added a carbon fiber, and then we oxidized that carbon fiber to leave a big hole in the middle of the membrane. So this membrane leaks. It doesn't work after this. But if we take the membrane through various stages of temperature, we can control the spreading of the molten salt, and it essentially acts like a sealant. The molten salt will move and reseal the membrane in a similar way to how your bones will heal over time if they're given time. So I'm not going to go through this very, very complicated plot. I would just encourage you to read this paper if you're interested in this idea of self-healing membranes. This was the first membrane that could self-heal without any human interference and without using any materials other than the materials that are already used to build the membrane. So if that's something of interest, I would encourage you to read this paper. So I've just been talking about the mobility of the molten salt itself. But the solid phases, we shouldn't forget, we're operating at very high temperatures. We're operating with molten salts. These are corrosive liquids. They can dissolve ceramics. They can dissolve metals. We need to bear in mind that the solid phase within the membrane may actually be moving as well. And this may influence the way that the membrane functions. So here what we set out to do, I said at the start that if we have a metal membrane, we'll get electron conduction in the solid phase, and that will mean we can permeate oxygen as well as carbon dioxide. So here we wanted to show that we could do that with a very, very small amount of metal. We don't want to build big membranes out of silver. It would be very, very expensive. We want to try and decorate a low-cost ceramic material with a metal, kind of in a similar way to how you'd make a catalyst, that you would decorate a ceramic with a small amount of metal. So in this case, this orange color on the bottom here is silver metal, and the black is alumina. So about the cheapest ceramic material you can buy. And what we were able to do is grow these structures, these silver structures versus time inside the membrane. And once those silver structures span between the feed and permeate side, you see that the electrical conductivity or the resistivity changes significantly, about 3 orders of magnitude difference. So no conductivity in this system, very, very good electron conductivity in this system. But we've been able to do this using a vanishingly small amount of silver. And we can do the same thing. I talked about the laser drilled structures with the beautiful parallel pores. So we can grow these same silver structures within these pores and get very, very high performance membranes. So the plot that I showed you on one of the early slides actually comes from this membrane. These points here, very, very high permeabilities, very high selectivities, comes from this membrane decorated with silver. So very, very high performance using low cost ceramic, but with a very small amount of a high cost metal. So I'm about 2/3 of the way through the talk, so I'm just going to summarize this middle section. So what I wanted to talk about was supported molten salt membranes, introduce you to what they are, talk about how they can be used to overcome selectivity, permeability, permeance targets for specific application, in my case, carbon dioxide capture. And then I wanted to tell you about the work that we do to control structure, control pore size, control the mobility of the metals, the ceramics, the molten salt within the structures to try and improve performance. I'm not going to talk about this in a great deal, but I think the open questions, the things that we don't know that we're still working on, are the specific permeation mechanism. So the exact intermediates, the species involved, we don't have a great understanding of this. And because these are new membranes, we've done very little work on scaling this up to look at real systems. I do think there's exciting opportunities for reaction engineering. Compared to polymeric membranes, we can operate at very high temperature and with very high selectivity. So I think that means that there's probably going to be nice applications in reaction engineering. But what I want to do for this final section is basically talk a little bit about reaction engineering and also talk about something I've just started working on, not necessarily with the same class of membrane, but just I wanted to leave you with a sort of exciting scientific challenge for anybody that's interested in chemical separations. So this image is maybe what the future will look like. Okay, I'm definitely saying maybe here. In the future, we might be forced to think about how we can close this carbon cycle. So when we produce CO2, wherever that comes from, and it goes into the air, how do we capture it from the air? Now, this is very, very difficult to do, right? It's 400 parts per million CO2 in the air. So it's very dilute. It's very, very difficult. But if we can do that, we can then use that CO2 to produce fuels directly from the air, and we close the carbon cycle. We should, of course, be thinking about renewable energies first and building lots of wind turbines and solar power. And then we should be thinking about, we need to be getting rid of fossil fuels and doing normal carbon capture. But maybe very far into the future, we might think about this for very specific applications. And here I'm thinking about things like aviation, for example. So first of all, I want to just talk briefly about membrane reaction engineering. I said at the start that we have a postdoc working in this area, sponsored by the UK Catalysis Hub. This is Guanan. So this is the kind of things he thinks about quite a lot. So from carbon dioxide, we can use it directly. We can make food and carbonated beverages, but we can also do chemical transformations to make synthetic fuels, to make polymers, plastics, solvents, etc., etc. And I think this manufacturing of synthetic fuels is probably where this will probably be very interesting in the future, because it's very, very difficult to get, battery-powered vehicles are now becoming more common, but it's very, very difficult to get a battery-powered international shipping container or a battery-powered passenger plane, because it's very difficult to get the power density required to get those things moving. So it's possible that we'll start looking at how we transform CO2 into these types of fuels. And these examples down the right here are all examples of supported molten salt membranes, where we take carbon dioxide out of a gas mixture, and then we use some sort of catalytic process to do a reaction. So this could be the water gas shift reaction, it could be for hydrogen production, it could be methane reforming. But the fact that the membranes I work on can be operated at 400, 500, 600 degrees, it starts to allow you to build catalytic membrane reactors. Very difficult to do this with polymer membranes because they typically cannot be used above 200 degrees. So I think there's some real interesting opportunities here for these types of reactions. And then I said I also think direct air capture is an interesting challenge for the future. So it's the idea of removing CO2 from the atmosphere. We're probably all quite comfortable or familiar with industrial CCS, so pulling CO2 out of a gas mixture. But pulling CO2 out of the air is extremely difficult. This image summarizes it quite well. We need a process. All these little balls are supposed to be the molecules in the air. So nitrogen and oxygen gives you 99% of what's in the air. And then CO2 is 400 parts per million. So you need a process that looks at all of these individual balls and says, no, 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 all the way until it gets to this one and it says yes. So what that means is it's extremely difficult to, or it's extremely energy intensive to process this great big volume of air. And it's extremely challenging in terms of kinetics and thermodynamics. and it's extremely expensive as well. So I said at the start that separations are very expensive. And this is definitely the case with direct air capture. We've got very dilute gas stream that we want to process. But that said, if we can do it, this process has been described as one of the 7 chemical separations to change the world. So I think it's a very important challenge. It's very exciting and something I would encourage you to have a look into. So at this point, I'm going to skip a few slides and I'm just going to wrap up. I'm going to skip these slides. So in conclusion, what I've tried to talk about, and I hope I've done a reasonable job of doing so, is why chemical separations are important, thinking about recovering resources, environmental remediation, producing the products we need every day, how we do them, and maybe that membranes are a better way to do this. They can be lower energy, and maybe we can also get inspiration from nature. I've introduced you to the idea of a supported molten salt membrane. It's the area that I work. And I've also tried to leave you with some, I hope, inspiring challenges for membranes in the future. So reaction engineering scenarios and direct air capture. And these 2 fairly recent publications will sort of give you a lot of the information that I've been talking about today. So with that, it just leaves me to once again thank all of you for attending, and thank you, Zeni, very much for the invitation. And again, just to thank all the collaborators on this work and the funders of this work as well. Feel free to email me with any questions or anything you want to discuss after the talk. And also you can find me on Twitter at MuchDoctor if you want to continue the conversation. But for now, I'm very happy to take any questions that anybody has.
Okay, thank you very much, Greg, for the outstanding lecture. Yeah. I'm sure that there will be a very enjoyable discussion after this. So ladies and gentlemen, and all students, if you have any questions, would you please use the feature of raise hand so that you can deliver your question directly to Greg, or you may also write down your question. I will be happy to pass it. Okay, any questions? Okay. So one question from our lecturer, one of our lecturer. Please, Mr. Srianda.
Okay, thank you. Okay, thank you. I'm sorry. Okay. Okay, sorry. Since we are in the same place at the moment.
No problem. I can hear you now, so that's good.
Okay. So thank you, Greg, for your course. Gratefully, we have a new insight about the molten salt for the case separation membrane, and it is very interesting because in your review, it is stated that in the molten salt membranes, we don't have to face with the trade-off anymore, because and we can reach actually the ideal, the dreams of all the scientists in the gas separation membrane to walk into the right corner top of the Robinson curve. So is it because the molten salt itself is the the mechanism is involved in the reaction with the molten salt, or it's just the physical? Thank you.
Yeah, no, you raise a very important point, and it's exactly right that the membrane operates on what's called a facilitated transport mechanism. So as long as you operate the separation under certain conditions, or you can operate under certain conditions, then you don't face this trade-off behavior. So I suppose the way to think about it, and a simple analogy that I often use when giving lectures in this area, if you think of a coffee filter and you have coffee grains, you put them in and you put the water and you get the coffee out the bottom. If I make the pores very large here, I get higher flux, but I also get the coffee grains, so I lose selectivity. In these kind of membranes, what we have is a very, very, very highly selective carrier. It moves through the membrane, picks up the CO2 and moves back through the membrane. And it will only move carbon dioxide. It has no reactivity with nitrogen. A very, very almost unmeasurable amount of nitrogen will dissolve in a molten carbonate. So that means that you've got almost infinite selectivity. So you cannot have that problem anymore. You cannot have that trade-off, because there is no selectivity for two gases. If you make a perfectly sealed membrane and it only contains molten carbonate, you have almost infinite selectivity. So how can you have a trade-off with permeability? Because your selectivity can't, it can't go any lower. So I agree, it's a very, very interesting property of the membrane. What you have to be able to do, that is only true if you have CO2 and nitrogen and you have a perfectly sealed, perfectly made membrane. If you introduce something like sulfur dioxide, oxides of nitrogen, these acidic gases will react with molten carbonates, and under some conditions you will get permeation. So if you think about CO2 capture, you would need to remove these gases first. But I still think if we take the typical membrane, a polymeric membrane, a polymer with free volume, you will get some nitrogen dissolving in that always. There's no infinitely selective polymer membrane. So there's obviously a lot of other challenges. Polymer membranes have been looked at for 50 years or a very long time, whereas this class of membrane, it's only been worked on by a very small number of people for a very relatively short time. So there's a lot less development and a lot of other challenges, how you fabricate nice membrane modules, this kind of thing.
Okay, thank you. And can I ask one more question, Miss Moderator?
Yes.
Okay. So it's interesting when you present about the preparation of the molten salt membrane. I'm sorry, from the alumina crucible. Is that right?
Yep.
So how did you make a pour for the molten salt on that particular? So you said from the laser etching or something like that.
Yes, exactly that. Laser drilling. So basically we fire a laser at the same point of the ceramic over and over and over until we drill a hole. So just like a normal power drill, drilling a hole, but it's using a laser. So we can get very, very small pores, very well controlled. So we've started doing this a lot. It's not necessarily something that would be useful in a real application because it's very expensive, but it's very useful in the lab because we get a very well-defined surface area. We know exactly where the molten salt is, exactly how much is in there, and exactly the surface area. So it's very useful for doing very precise experiments.
Okay. Is there any particular specification for the laser? Right. I mean,
for the
wavelength?
laser, you said?
Yeah.
I would need to look into that for you. That's not my expertise. I would need to, feel free to give me an email and I can put you in touch with the person that does the laser drilling. I'm not sure about that.
Oh, okay. Thank you. Thank you very much for your kind answer.
No problem. Thank you for the questions.
Okay. Thank you very much, Mr. Trianda. So any more questions from the other attendants? Okay, so one more question from Bunuru.
Okay, thank you very much. I'm interested in particularly in solid phase mobility. As you mentioned that the growth of silver structure inside the membranes. My question is how to control the growth of the silver structure inside the membrane and what the parameter to control it?
Yeah, that's a really, really good question. So I think it's a very interesting effect. We actually control the direction of the growth by using chemical potential difference across the membrane. So if you apply an oxygen chemical potential difference across the membrane and you have silver on this side, oxygen encourages the oxidation of the silver into the molten salt. And then because there's a gradient in oxygen, it actually encourages it to grow through the membrane. So the mechanism is explained, at least an initial mechanism, we're still working on this and still interested in how it occurs, but certainly the silver will only dissolve into the molten salt if there's oxygen present. If there's no oxygen, it doesn't dissolve. So when the oxygen's present, it's oxidized, it dissolves, and then because there's a difference in oxygen across the membrane, that's why the silver will move. So what that means is that you could actually imagine a system that potentially over time, all that oxygen is going to move across the membrane. But then if you switch your feed and permeate sides, you could force that silver to grow back the way. So that's what we're working on at the moment. We're trying to see, can we control the movement of a metal within a ceramic matrix by using a chemical potential difference across in terms of the gas composition.
So that mechanism is always similar if we use other metals.
It's a good question. So we looked at silver and we looked at gold, and we did not see the effect to the same extent with gold. You see some corrosion with gold, but not as much. And we think that there's a few different properties that are important here. One is the solubility of the metal in the molten carbonate, and the other one is the electronic conductivity, because it's all about electron transport. So we think silver, higher electronic conductivity, and also a higher solubility in the molten carbonate. But that said, if you use different molten salts, you can control the oxidation potential, the corrosivity, the pH, whatever you want to think of it as. You can control that by using different molten salts or different mixtures. So potentially you could do this with other metals, but we haven't looked at that.
Okay, thank you, Greg.
Thank you very much for the question.
Thank you very much, Bu Nurul. Any more questions? I think one more question from the student, maybe. So there is one question that they are a bit scared to say directly.
Don't worry. I promise I'm not scary. I'll be very friendly.
Yeah. So, there's one person there.
Oh, we've got a brave person. Well done. Well done to you.
Okay.
Thank you. So
Please,
my name
Afi,
is
what?
yes. Thank you. So my name is Afi. Can you hear my voice?
I can hear you loud and clear.
Okay, thank you. So in the in my master degree before, I create the lithium-ion battery, solid lithium-ion battery, and I create the membrane to spare it and to transport lithium-ion from anode to cathode. And my problem is that because the membrane is not really good. I don't know why I cannot create the good membrane to transport really good lithium ion to anode and cathode. And I changed to my ways to create the membrane with the good electronegativity, and then it will be catch the lithium ion. But the problem is that in the transport phenomena, the lithium ion will be stuck in the membrane. So I just want to discuss what should I do for my research about that. So what should I need to modify my membrane become good transport from lithium ion from anode to cathode.
Yeah, so I have to admit that lithium-ion batteries and lithium-ion transport is not my area of expertise, but I think I can tell from the way that you're talking about the problem that you have a very good understanding of what's occurring. So of course you need to think about the properties that we've been discussing in this talk. So ionic conductivity, good connectivity between the different particles within the membrane so that you get good transport. You need to start thinking about grain boundary diffusion and resistances to diffusion within the structure. So I would say that probably you want to characterize the material in a very detailed way so that you can understand the different factors that might be limiting transport of lithium. But that's a very general answer. And it obviously also relies on being able to access the kinds of techniques that will allow you to look at those properties. I'd be very happy to follow up on that by email if there's anything that you think you would like to try and do in terms of the experiments, or also if I can give you a better answer with a little bit more time.
Yeah, thank you, Dr. Gray.
And thank you very much for being the brave one to ask the question.
Okay, any more questions? Thank you very much, Afi, for the question. One more, probably. Oh, there is one more question.
Yeah, I'm reading the one in the chat. If you give me 10
Okay.
seconds, I can read it. So this person is interested in the use of membranes for direct air capture, particularly for CO2 utilization. In the CO2 reaction, there's a side reaction such as reverse water gas shift. Is there a way to overcome this when we want to design a membrane? These are exactly the kind of problems that we're working on at the moment. We're looking at how we can use membranes in water gas shift, reverse water gas shift, dry reforming of methane, how we can pull CO2 out of very dilute streams. So I don't have a specific answer to this question, but I would just strongly encourage you to keep working in that area because I think it's a very exciting area, lots of opportunities to do really good work.
Okay, thank you very much, Greg. Unfortunately, our time is limited, so we have to end our discussion. Before we close this lecture, I would like to remind everyone again, please don't forget to register because we will send the certificate by next week, inshallah. So on behalf of our committee, oh, okay, sorry. Okay, before we close our discussion, we would like to take picture together, if you don't mind. Okay, so everybody please open your camera, turn on your camera so we can take picture together. Yeah, I will count to 3, yeah? Okay, everybody is ready or oh, not yet? Okay. Okay, 1, 2, 3, cheese. Okay, one more. 1, 2, 3. Okay, did you get it, Pak Trianda? Okay. Okay, so on behalf of the committee, I would like to thank our lecturer today. Thank you very much, Greg, for your outstanding talk. Yeah. I'm looking forward to our next collaboration, hopefully in the near future. And for everybody, thank you very much for joining and see you again in the next guest lecture. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Greg. See you all.
Thank you very much, everyone. It was lovely to meet you all. Thank you very much and have a